How can the universe contain a whole so vast that thousands of galaxies seem to be missing? In the constellation Boötes, astronomers have found a region so empty that it challenges our basic picture of cosmic structure. It is called the Boötes Void, or more dramatically, the Great Nothing. This is not an absence of space, it is an absence of the galaxies that space was expected to hold. The void stretches roughly 330 million light-years across, making it one of the largest known empty regions in the universe. Light itself would need hundreds of millions of years to cross it. Within that enormous volume, galaxies are extraordinarily scarce. The silence is not absolute, but compared with the crowded regions around it, the Boötes Void is almost a cosmic desert. To understand why that matters, we must understand cosmic voids. The universe is not arranged randomly. Galaxies gather in clusters, chains, and vast filaments, forming a web of matter across space. Between those structures lie voids, regions with far fewer galaxies than average. Their emptiness is expected. The Boötes Void is unsettling because its size and apparent isolation seem far less ordinary. The galaxy distribution is the visible pattern left by gravity acting over cosmic time. Matter was not spread perfectly evenly after the Big Bang. Tiny differences in density gradually grew. Gravity pulled matter toward denser regions where galaxies and clusters formed, while surrounding regions were depleted. That general process explains many voids, but it does not easily explain one apparently large enough to contain thousands of missing galaxies. The first clues emerged through astronomical surveys that mapped galaxies by measuring their positions and distances. These surveys do more than count points of light. They reveal how galaxies are arranged through three-dimensional space. As the maps expanded, an unusual gap appeared in the direction of Boötes. What seemed at first like an incomplete observation became a persistent feature in the cosmic record. That discovery raised an immediate question. Was the void truly empty, or had astronomers simply failed to detect what was inside? Dust can hide objects. Instruments have limits. Distances can be misjudged. Yet repeated observations supported the existence of a genuine underdense region, meaning a volume containing much less matter and far fewer galaxies than the cosmic average. Even so, the word empty can mislead us. The Boötes Void still contains space, radiation, and the faint ingredients of the universe. It may also contain dark matter, the invisible form of matter inferred from its gravitational effects. What is missing is the dense population of luminous galaxies that normally traces the underlying structure. The void is therefore not nothing. It is a profound shortage. How could such a shortage develop? One possibility is that the Boötes Void did not begin as one immense emptiness. It may have formed when several smaller voids expanded and merged. As matter moved outward toward surrounding filaments and clusters, the low-density regions could have joined together. Over cosmic time, separate hollows might have become one enormous chamber of relative emptiness. That explanation fits the general behavior of voids, which tend to grow as matter flows away from them. But the Boötes Void remains difficult because merging smaller voids requires the surrounding cosmic web to evolve in a particular way. The timing, geometry, and amount of matter involved must all align. A possible pathway is not automatically a complete explanation. Dark energy adds another layer of uncertainty. Dark energy is the name given to the unknown influence associated with the accelerating expansion of the universe. As space expands, the growth of enormous underdense regions can be affected. Some cosmological models suggest that dark energy may help voids become larger and emptier over time. Yet it does not function as a simple vacuum cleaner, removing galaxies from a prepared cosmic whole. The deeper story begins with the Big Bang theory, which describes the universe expanding from an early, extremely hot and dense state. The theory does not predict a perfectly uniform cosmos. Small variations in the early distribution of matter became the seeds of later structure. Galaxies, clusters, filaments, and voids emerged as gravity amplified those differences. The Boötes Void is one result of that history, but perhaps an unusually extreme one. Here the mystery becomes more precise. The question is not whether gravity can create empty regions. It clearly can. The question is whether known cosmic evolution can create a void of this scale, in this location, with so few galaxies inside it, without requiring conditions that current models consider unusually unlikely. The void may be possible, yet still statistically surprising. A few galaxies do exist within the Boötes Void. Their presence is important. If the region contained absolutely nothing, it would be easier to treat it as a boundary problem or an observational mistake. Instead, these sparse inhabitants show that matter is not completely excluded. They occupy a rare environment, surrounded by immense distances and far removed from the crowded neighborhoods where most galaxies reside. Those galaxies also provide evidence about the void's history. Their properties, positions, and relationship to the surrounding structures can help astronomers test how matter moved through the region. A void is not merely defined by what it lacks. Its edges, internal traces, and neighboring filaments preserve clues about the forces that shaped it. Emptiness becomes a record of motion. The Boötes Void therefore tests the statistics of cosmology. In a universe governed by probability, rare structures are not impossible. A highly unusual outcome can still occur somewhere across an enormous cosmos, but when an observation appears too extreme, scientists examine every assumption, the survey methods, the distance estimates, the models of galaxy formation, and the influence of dark energy. That process is not a failure of science. It is science working at its most revealing boundary. A model earns confidence by explaining ordinary structures, but its deepest weaknesses may appear in extraordinary ones. The Boötes Void forces cosmologists to ask whether the standard picture fully captures how matter clumped together after the Big Bang, or whether some part of that story remains incomplete. Beyond Boötes, cosmic voids help define the universe as much as galaxies do. The luminous structures are only the ridges of a much larger pattern. The emptiness between them shapes how matter is distributed, how gravity operates across immense distances, and how the universe expands. What appears vacant is actually part of the architecture. The cosmic web is built from both presence and absence, and the void offers a strange lesson about scale. On Earth, an empty region may mean a missing object or an unvisited place. Across the universe, emptiness can span hundreds of millions of light years and persist through deep time. The absence of galaxies becomes an astronomical event, not because nothing happens there, but because the surrounding universe reveals how much should have happened. We do not yet possess a final explanation for why the Boötes Void is so empty. Merging voids may contribute. The expansion driven by dark energy may influence its growth. The uneven beginnings described by Big Bang theory set the initial conditions. Together, these ideas form a framework, not a finished answer. The remaining uncertainty is precisely what makes the void scientifically valuable. In the Great Nothing, we encounter a universe that is not random, yet not perfectly predictable, structured, yet filled with exceptions. The Boötes Void is a missing crowd written into the map of creation. Its darkness does not erase the cosmic story, it preserves one. By studying what failed to gather, we learn how galaxies formed, how space expanded, and how much remains unknown in the vast architecture of the universe.